Hi everyone, this is the last part of capacitors, and it has to do with charging and discharging a capacitor. We're going to start with the discharging of a capacitor. So this is a simple setup of how you can investigate how to discharging of a capacitor. So what you have is a power supply or a cell or battery that gives you the maximum voltage that you will have across your capacitor once you fully charge it. Just once again, a reminder, here you will have a buildup of negative charge, and here it will be a deficiency of electrons, so it will lead to a positive charge on that side. Now, if I place a voltmeter, so I have a switch here, and the purpose of the switch is to simply allow us to fully charge the capacitor so we can have the correct value of voltage. And then to make sure, because we have the capacitor connected in parallel with the resistor, we'll also connect parallel to them a voltmeter, which will simply give us the voltage across the capacitor, which is going to be the same as the voltage across the resistor since they're in parallel initially. So at time t0, just about I fully charge my capacitor. So my capacitor is fully charged, and it has a potential difference of V0 across it as soon as it's firstly charged. The fact that we're discharging it, so the stored charge across it here, it will be discharged, so it will be allowed to flow around the resistor. This happens only when I open up the switch. So let's start with slowly breaking it down from the very beginning. So once again, my capacitor is fully charged when the switch is closed, and at time 0 seconds, so I'll take time 0 seconds to be the moment I open up the switch. So I will simply now open the switch. And we said at time 0, the potential difference across the capacitor is V0. And the same thing, the potential difference across the resistor is V0 during this time. Now once I open the switch, this part of the circuit is no longer part of the circuit, so it's like completely broken out and cut out. So what I have is the capacitor and the resistor actually being in a complete circuit of their own, and the voltmeter just getting the voltage across them. So let's continue with what happens after the time 0. So to begin with, fully charged at time 0, I open the switch, and immediately what you will experience is this voltmeter will start dropping the number. Why does that happen? Let's see. There's 3 key values we will focus on in this. One of them is the voltage across the capacitor and the resistor, the charge across the capacitor, which can be simply given by Q is equal to V0 C from the equation of capacitance, which is the charge stored per unit voltage, and also the current that actually flows through the resistor. So this is for the capacitor. And then I have the current flowing through the resistor, which is based on the resistor, because I'm using the resistor to discharge my capacitor. So as soon as I lift the switch open, what I have is the electrons flowing around through the resistor, discharging, and eventually leading to no charge stored across the capacitor. So it will discharge through the resistor. Now this happens, the charge across the resistor decreases over time, obviously, because obviously we said that it's going to discharge through the capacitor. So over time, this charge is removed. The overall charge is removed. It balances around in the circuit as it goes through the resistor. And we also know that current is the amount of charge flowing past the point per unit time. So that's another quantity that with time will decrease. So we have these two quantities are decreasing with time. And that's due to the fact that we know that the charge here will be allowed, because the battery is no longer forcing the charges to remain there. As there's no charges remaining there, they will reach 0 once it is fully discharged, and the current obviously will reach 0 because the charges will no longer be flowing per unit time. So this is a good point to relate it back to these two equations so you don't forget it. Now, why does the voltage across the capacitor decrease to 0? Well, firstly, to begin with, we know this equation right here. Since Q is equal to CV, capacitance, the capacitor is the same capacitor, so this capacitance doesn't change, the constant number, which means Q is directly proportional to V. So as time goes by, if charge decreases to 0, so will voltage decrease to 0 across the capacitor. The same thing will be seen as there's no current flowing through the resistor anymore after a certain amount of time when the charge is 0. This will also show 0 as well. So what we expect is the voltage across the capacitor, the voltage across the resistor after a time t. They will all go to 0, including the charge of the capacitor and the current through the resistor. So that's simply discharging a capacitor. But we are deeply interested in how this changes with time. So how do these quantities change with time? By the way, it doesn't have to be a resistor. It could be a little LED, little light bulb. It would, for a very small fraction of a minute or seconds, be bright, the light, so it will light up, and then you'll see obviously that it discharged by the light not being on anymore. So we can't just transfer energy if there is no energy there. So that's the important part to always remember. Now, what's the equations that you should be aware regarding this? In the actual books, you're given, I'm going to show you from the exam board. So equations in the form this. X is equal to x naught e to the minus t over CR. In other words, you will be given this in the formula booklet. If you even go back to your books, it's given to you in the formula booklet that you will be provided in your exams, but you will not be given the specific ones regarding the voltage, the charge, and so on. You will have to make the correct choice when it comes to that. So that's the exact formula that you will be given regarding to discharging a capacitor, and then we'll talk about charging a capacitor and how these values vary as well. So in other words, what you have is the voltage across the capacitor at a specific point in time is equal to the initial voltage that you started with times E, which is an exponential function. Do not confuse it with elementary charge here. So remember, we said the charge of an electron or a proton is based on the elementary charge of 1.6 times 10 to the minus 19 coulombs. Well, don't confuse it with this. This is not what this E stands for. The number is just an important number, and it's the base of natural logarithms. And its actual value, if you put it on the calculator, is a button e to the x. If you put that in the calculator, if you press on that, it will give you a value of 2.718 and so on. So it's an irrational number, just like similar to pi. So please don't mix that up with any of these other values that we're going to talk about. So I'm just going to get rid of it for now because it's just going to make it look messy again. So we're going back to the equation. which is E times E to the minus T over CR, or RC is the same thing. Now, what do these stand for? This is the voltage or potential difference after time t. This is the time t that I will want to know. For example, if what would be the potential difference across my capacitor after 10 seconds or after 0.1 seconds. So this is what I will be calculating on this side if I'm given the time and all the other values. This is the initial potential difference across the capacitor when it's fully charged. And then you have C, which is the capacitance of the capacitor, capacitance of the capacitor. And this is the resistance of the resistor that the capacitor is discharging through. So this is the basics of the equation. So this is how voltage will be varied after a certain time t if I know my capacitance, the resistance, and the initial potential difference. Similarly, can calculate current. So here again, having the initial current at the very beginning of the circuit when I open the switch and allow current to flow through the resistor. This is after certain time t, capacitance of the capacitor, resistance of the resistor, and this is the current I can measure after a certain amount of time. And then we can do that again for charge. Now this is, before I continue to the charge, this is the voltage that can be calculated across the capacitor or the resistor at any given time. Then we have the charge. So this is the charge after a certain time. This is the initial charge stored across the capacitors times the exponential function e minus to the power of minus t over CR. I will also explain in a second the importance of CR, and it's going to be a very, very big part of all our calculations and an important understanding of the topic. So you can also show this graphically. They will all look the same as a graph. Obviously, the values will be different because you can't have the same voltage and current and charge. They vary. So graphically, it will look, for example, it was a voltage against time graph. This is an exponential decay, and I'll explain that in a bit. It can be drawn as a line like this. So here will be your initial voltage, the starting voltage of the capacitor, and eventually it will fall with time in an exponential decay. The same graphs will look for current, so that instead of that being I, that will be I naught, sorry, V will be naught, could be Q, and that will be Q naught. All three look the same for discharging because all the values are dropping together to zero as the capacitor is discharging through a resistor. It's a bit different from when it's charging, and we'll talk about that as well. So many of you might be a bit confused as to what you can do with these equations. I'll show you a simple example, and then I will go into how we can represent these lines, these curved lines with equation of a straight line. So showing it as a straight line because it's easier for us to work with straight lines and gradients as well in physics. So we prefer the straight lines, especially since you already know how to manipulate that. But the new thing will be that we'll be introducing natural logarithms. So just bear with this lesson. Okay, let's start with the example. So what we have is 400 microfarad capacitor. So we know the capacitance already. It's very important to label if you want, or even make a list of your values. It doesn't matter which way you prefer to do it, as long as you do it, because it makes you see clearly the picture. And it says it's fully charged to a potential difference of 10 volts. So that's my V naught, because that's my initial potential difference. It discharges through a resistor of resistance 100 kilo ohms. So my resistance is 100,000 ohms, because a kilo is times 10 to the 3. Here we have microfarads, which is 470 times 10 to the minus 6 farads. Don't forget about your unit prefixes. It says calculate the initial current, so I need to find I naught first. So I have the initial voltage, I have the resistance of the resistor, so I can find I, because I know an equation that links all three together. So in this case is V over I, which gives me I is equal to V over R, and you get 10 divided by 100,000, which is about 1 times 10 to the minus 4 amps. And the next part that you need to calculate is the potential difference across the capacitor after 30 seconds. So another important part, after 30 seconds. So I'm looking for the PD after 30 seconds, hence I will need to use the equation that links PD to time. And this is my equation. So I start off with the voltage, the initial potential difference, 10 e to the minus after 30 seconds, so that's minus 30 divided by C times R, so C times R, which is 470 times 10 to the minus 6 times 100 times 10 to the 3. You can do simple breakdown of the power, so that will be 10 to the minus 3, and then you have 3 extra zeros, so that will give you 10 to the minus, so let me do it quickly. So combining these two gives you 10 to the minus 3, but then I have 2 more zeros there and another one, so it's kind of like saying 47 times 1,000 again, but 1,000 times 10 to the minus 3 is 0, so that's 47. You don't have to do that in your brain, you can do it quite quickly if you want, but you don't have to. You can rely on your calculator. So this is my expression. As soon as I put it on the calculator, I get a value of 5.3 volts to two significant figures. So you can see that it shows me that my potential difference after 30 seconds of discharging the capacitor, I have 5.3 volts left across it. So the energy is decreasing with time in an exponential manner. So what does exponential decay actually mean? So in case of a voltage, let's say, so I have the voltage against time of a capacitor as it discharges. What you will notice is for the same amount of time interval, let's say we pick 10 seconds. This is just an example, this is not accurate and very precise. So let's say for for an equal amount of time interval, the quantity, the voltage is actually decreasing by the same factor. Now this is going to be also seen, we're looking at it now in capacitors, but we're also going to see it in radioactivity with half-life. We will see it in other topics such as simple harmonic motion, but not as much as in detail. So we said that the actual voltage decreases by the same factor in equal time intervals. For example, if this is V0 and this is V1, then this will be V2, this will be V3, this will be V4. I want you to notice that firstly, I have equal time intervals between the actual numbers I've marked on the y-axis. And if you get the numbers from any graph, and you can do that with any graph that's in your books that's got labels already on it, and you can practice it, or even example questions that we're going to look at. So if I get V1 divided by V0, and I get V2 divided by V1, I get V3 divided by V2, and so on. V4 divided by V3. Now, all of these ratios will be roughly equal. And that's what we mean by this constant ratio pattern, which we call exponential decay. So exponential decay shows a constant ratio pattern, and in this case is in regards to time. Sorry, in equal time intervals. Okay, so now this is a very important bit that I said before that we will be focusing on, is the part of the equation that's the CR. So in other words, this part of the equation. Now that's actually called the time constant. Let's start with that. The symbol for a time constant is the Greek letter tau. It's actually called DAF, but let's call it tau. And it's actually equal to CR, which is that number that we saw in one of these equations. So instead of writing it like this, you can also rewrite it as this. And it has a very, very specific meaning to us. So that's why it should be the hero of this topic in a way. It should be one of the main characters in this topic. Before I move on to explain what time constant is, I wanted us to focus on this section here. Now, the time constant's unit is actually seconds, and we can prove that quite easily. So if the time constant is equal to CR, and capacitance is equal to Q over V, resistance is V over I, then what I end up with is Q over I, and I also know that I is Q over T. So what I have is now tau is equal to Q over T, which is the same thing as saying Q times T over Q. So this cancel, and we know that the units of time are seconds, so the unit of time constant is seconds too. Hence why when we look at this equation, the units that we get for voltage is still going to be volts, because this actually seconds per second, which is just a fraction, doesn't have units. So we only consider the units of the voltage in this equation. But this is a general equation anyway. It could be for current, it could be for charge as well. But it always cancels out because the unit of time is seconds. Now, the importance of the time constant. What we have, time constant for a discharging capacitor. This is very important because for a charging capacitor it's different. So for a discharging capacitor is equal to the time taken for the potential difference or current or charge to decrease to 37% of its initial value. And that means that if I equate the time here, so if I equate this time and say, okay, how much potential difference will I be left with after one time constant? So after one time constant amount of time has passed, then I can rewrite this as V is equal to V naught e to the minus tau over tau, which tau over tau is equal to 1. So that's V is equal to V naught e to the minus 1. Now, if you put that in your calculator, if you put e to the minus 1 in your calculator, you will end up with something that's 0.37 V naught. Hence why we're saying that the time constant for a discharging capacitor is the time taken for the potential difference to decrease to about 37% of its initial value. So this is the 37% of the initial value that I started with. So now, is this one way that we can model this exponential decay from the very beginning? And that's to consider what takes part, like we did at the very beginning of this lesson. So we started off with having a power supply parallel with a capacitor, in parallel with a resistor. You charge it, then you disconnect it, and you're left with the capacitor and the resistor being parallel to each other. Now I can figure out the charge stored by the capacitor, which is given by Q is equal to Vc. Remember, it's just simply the capacitance equation just rearranged. And I can also have an expression for the current that's in the circuit, which we also know how it's linked to resistance, so IV over R. And I know that since both of the resistor and the capacitor have the same voltage, since they're in parallel to each other, then I can substitute this equation in this one. So I will be having V is equal to Q over C as a rearranging and substitute it in there. So that will give me I is equal to QCR. And since in a capacitor, the capacitor is actually losing the charge. So we need to add for the capacitor, I is minus the change in charge divided by the change in time. Once again, mentioning here, it's because the charge on the capacitor decreases with time. That's why we're including that negative sign. Now I will simply just substitute also this equation into this one, because I is equal to I in that case. So I end up with change in Q over change in T. I'm just moving my negative side to the other side of the equation. It doesn't matter exactly where it is. And this is the equation that you can use is a very simple equation to use to basically model the decay of charge on a capacitor. And we call this method iterative modeling, and I'll go into it at another moment. So now the next bit I'm going to talk about for the next couple of minutes is not necessary for your course. It's only for those of you who are interested in integration and where this equation, so where did this equation, for example, come from. And this is actually, this exponential decay is the solution for this equation. So you don't need to know how to get from this to this, but you do need to be able to use them separately. So what we have to start with, we start with this equation. So this is a simple way of showing the exponential decay, so modeling it. Now this means a change in Q divided by change in T. Now if I consider a very, very small change in Q divided by a very, very small change in T, I can rewrite the equation as dQ dt is equal to minus Q over CR. And many of you might already know how to deal with this. In this case, we have to rearrange and keep, for example, Q with the dQ side and dt on the other side. So we rearrange to keep dQ 1 over Q, and the dt will go to the other side, and I will integrate both sides to reach the solution. So that will be 1 over CR. I have a minus sign, and I will rather keep the minus sign on this side. So we are integrating from time 0 to time t, and from q naught at time 0 to q at time t. Now when we do integrate this, we get ln q with the limits of q and q naught. So at time t you have charge q, at time 0 you have q naught, and then you have minus t over CR with respect to time there and there, t and 0. Once you do the quick calculation, that's going to be ln q minus ln q naught. That's going to be minus t over CR. And if I put 0 into t, that will be 0, so I can ignore that. Now I will actually rearrange my equation to make it a bit simpler to get to the original one that we know the solution is. Like I said before, this is not needed for you to know how to solve this equation to get to this. I'm just showing you the steps here for those of you who are doing more maths and are more interested into this part of the video only. Now with the logarithm rules that you should know, we have ln q over q naught. I will go into this in a second more deeper about the rules and what you should know about this, and that's equal to minus t over CR. Now what I will just do, the next step is to raise this to the e power, so it will be e ln actually cancels out, so it will be q over q naught. I will explain that once again, like I said before, and e to the minus t CR. So from there, you just simply rearrange and you come to the equation that we need to know. Once again, like I said, this is not something that you should know, but it is a good thing to know that this is where we start from. This is the equations that link directly to the current, capacitance, resistance in the circuit, and how when we solve this, we come to this equation. You do not need to know it. It's just a little bit of extra bit for those who are doing more in the mathematics section and are interested in this. Now, the rest of the things I'm going to talk about, you do need to know, so do pay attention. I'm going to explain a bit about the mathematical side of this topic now, because we will start getting into it a bit more. And I will start with certain things that you already know and are simple to you. So we usually have, in a simple equation, we have a base number. It could have a power, and that will give you the actual number. So once again, that's the base, that's the power, and this will give you the number that these two other numbers are equal to. So for example, 2 to the power of 2 is equal to 4. So this is your base, this is your power, and this is your number. If you want to solve for weirder numbers that you're not used to, like really big or really small numbers and so on, or even see this expression in a different way, we can write it in a logarithmic form. So for example, log base number is equal to the power. So once again, this is the base, this is the number, and this is the power. So this is another way of writing this expression in a logarithmic form, in this form. So don't think that logarithmic expressions are something extreme or something crazy. But in general, this is the exact form that is following. So if I wanted to rewrite this in a logarithmic form, so 2 to the power of 2 is equal to 4, then I will have to write log my base, which is 2, my number, which is 4, is equal to the power, which is 2. So these two expressions are basically the exact same thing. Now, why am I saying this? Because we have to know a few rules regarding this. So that's the link to powers and logs. And I will talk about a few logs. So there's a general log that usually we won't see logs of 2 or things like that in maths. You're probably going to see log 10, which simply means the base is 10. So for example, if I had 10 to the power of 3, I know that's 1,000. So I can rewrite that as log 10 because that's my base. The number is 1,000. And if I put that in a calculator, I should actually get the power, which is 3. In what we will be working on, because our, in this case, we have e, so the exponential function. And we call this log, let me rephrase that. So what we will be working with is the natural log. So a log with base e. So instead of writing, for example, log e, we're going to write ln e, well, ln. And in other words, if I wrote ln e or log, actually let me leave that simple there, ln e, ln. Log e is the same thing as ln e. Now, if I wanted to write ln e, that means it's log e, well, log base e, number e, which is equal to 1. So the first rule is that ln of e is equal to 1. And that's, if I rewrite it now in the power form, so in this form, remember, our base is e, so it is e to the power of 1. So e to the power of anything is, e to the power of 1 or anything to the power of 1 is simply e. So hence why ln e is equal to 1. Now I want us to look at the rules that are actually within your book, because you are given them and you will be given this in the exam. It will be in a formula booklet. The first rule is that log a b is equal to log a plus log b. Now, if I'm multiplying two values together, that's what it is. If I'm multiplying them, then I have to add the log of each one. If I divide them, so log a divided by b, then I have log a minus log b. So I'm dividing here and I'm subtracting. So it's just simply expressions that you write down that do make sense if you put numbers in them. But it's better to know them in this way because we don't usually use a lot of numbers. We actually tend to rearrange our equations and then put numbers in them. So it's just simple rules that are given to you that you should be able to apply. And then we have two more rules. So log x to the power of n. In this case, we multiply the power by the expression, n log x. And like I said in this section here, if I have ln, because remember, ln is the same thing as a log with base e, and the number e is 2.71, so on. So ln e kx is equal to kx, because what this means, we already said that ln e is equal to 1. Now, if that had a power, ln kx, that means it will be kx ln e. We know this is equal to 1. So kx ln of e is equal to just simply kx. So this is basically what this is saying here. So these are the relationships that you do need to know. Remember, these are not some very, very complicated expressions. It's just simply a power expression rearranged in a different format so we can solve for it. So why do I even care about this? Well, like I said before, if I want to be able to solve a graph or write my expression in a straight line, so if we say we have V is equal to V naught E minus T over CR. Now this is an exponential graph. This is very hard for us to analyze or do anything in any other order. So what we prefer to do is turn this into an equation of a straight line. So y is equal to mx plus c. In order to be able to do that, we have to act on this equation. So what we can do is take the log of both sides to the base of e, because we are working with base e here, with an exponential function here. So what it will turn out to be is ln v is equal to ln, because I'm just going to put this in brackets so you know that I'm just putting them in equation, ln of v naught e to the minus t over cr. And here I'm going to use my one of my rules for this part. So this is ln v naught e to the minus t over cr. Now this is multiplication, right? And we know that if ln a times b, then ln a plus is the same thing as ln a plus ln b. So I will rewrite this. I have ln v is equal to ln v naught plus ln e minus t over cr. But then again, we know something else about this expression. So if I have ln e, log base e, then is equal to 1. So that leaves me with, e is equal to 1. So that leaves me with ln v is equal to ln v naught. This whole expression here disappears and I'm left with this one only. So I have minus, because it's plus, minus t over cr. You do need to be able to do this, and you do need to show your steps. At least these steps here are more than enough. This is me going a bit extra with these things to prove it to you. So do please, you should be able and expected to show this and do it. And now I can relate this to my equation of a straight line. So I know that I will need to plot log v, against time. It's quite similar to this graph, but instead of having v, now we have to turn all of our v values to ln v values. So that will be my y value, and this will be, let me rewrite it actually. So that will be my y value. This will be my x value, because this is the y-axis, this is the x-axis. That means whatever's next to x, so since y is equal to mx times x, then that means my 1 over cr is equal to my m, my gradient. And that leaves us with the plus c, and before I continue actually, the negative sign shows also that the gradient will be decreasing. And then since I have plus c, in this case my plus c will be the ln v naught. So in other words, you should expect to get a graph that's straight, crossing this part, which is ln v naught. Your gradient, so you're changing y divided by your change in x, will give you 1 over cr, and obviously ln v and t are your axes. So this is exactly what you do need to know, and you should be able to get values from it. Sorry, the gradient is minus 1 over CR. And the y-intercept is ln v naught. So the very, very important parts of an equation of a straight line. So very important as well, from the gradient, we said that you get 1 over CR, and we know that C times R is the time constant. So from the gradient, we really get the time constant if we take the inverse of the gradient. Okay, so this is the analysis of charging a capacitor. We have, instead of having a parallel circuit, in this case we have a series connected circuit with a power supply or a cell or battery, a capacitor with capacitance C, a resistor with resistance R, and initially we have the switch open and the capacitor is not charged at all. So at time 0 is the time when we're going to press the switch. So we're going to close the switch to charge the capacitor. Before I start the analysis, I wanted to remind you of Kirchhoff's law, where we have the power supply V naught is equal to VR plus VC. Remember the potential difference across a closed loop is equal to the EMF across a closed loop. The sum of EMFs across a closed loop is equal to the sum of the potential differences across a closed loop. That's what Kirchhoff's second law said. So by that law, if I want to write an expression at any time in the circuit, V naught is equal to VR plus VC. And that's a very important part of this analysis. So at the beginning, when I close the switch at time 0, I will have the highest current. But as time goes by and the capacitor, so once I close the switch at time 0, the charge starts building up across the capacitors plates, and the current in the circuit decreases because from the moment that the charge starts building up, it means that there's less and less electrons flowing per unit time. Hence, the current, once the capacitor is fully charged after a certain time, the current will reach 0. So in this setup about charging the capacitors, the current decreases from a maximum value. So current goes from max value to 0 when fully charged, when capacitor is fully charged. Now let's talk about the charge as well. Now we know at time 0 there's not as much, there's not charge on the capacitor plate, so charge is 0 to begin with, and then it increases to the maximum value that it can store. So in this case, charge increases across the capacitors. Current is through the whole circuit, so through the resistor and through the capacitor. And we know that once charge is built up across the capacitor, the voltage across the capacitor will go from 0 to maximum value across it. The next point, so to V naught actually, to V naught, because we have the value there. But while this is happening, so while I have my the potential difference of the capacitor increasing in the circuit to V naught, the potential difference of the resistor decreases this time because they're not in parallel, so they're not both getting the same amount of potential difference. The one has to increase, the other one has to decrease. For example, I'll give you numbers. If my potential difference, if my EMF, my electromotive force was 12 volts, and midway or 3/4 of the way of charging, let's say. This is just all hypothetical numbers. The voltage across the capacitor reached 8 at a specific time, then that means that my voltage across my resistor will be 4. But if I fully charged it, then that will lead to the if I fully charge the capacitor, that will mean that the resistor has 0 volts and the capacitor has 12 volts. So that will give me the voltage of the EMF. So we said after a long time, VC will be equal to V0 and VR will be equal to 0. So we said current decreases to 0 when fully charged. Charge goes to max when fully charged. VC, so the potential difference across the capacitor, will reach the potential difference of the EMF. And in this case, VR tends to 0. And this is where we're going to talk about the things that are happening in terms of equations. So since current is decreasing, I can still use the same equation we used for discharging a capacitor. But in the case of the resistor as well, the potential difference across the resistor, since it decreases, we can also express this as V0 e to the minus t over CR. So V0 being the maximum value in this case, and I0 being the initial current that was really high in the circuit. And since we know this expression here, so we know that V0 is equal to VC plus VR. I will substitute this in there. So it will be V0 is equal to VC plus V0 E minus T over CR. And I'll rearrange and take a common factor out. So it will be VC is equal to V0 minus V0 e to the minus t over CR. Take the common factor, and that's 1 minus e minus t over CR. Expand the brackets, you get the same thing, V0 minus V0 e minus TCR over CR, sorry. So now we have the expression for the potential difference across the capacitor, the potential difference across the resistor, and the charge across the resistor. We also know that in a capacitor, C is Q over V, and therefore that means that Q is CV, which makes Q directly proportional to V. Hence, in this case that I'm charging the capacitor, the charge is increasing just like the potential difference is increasing on the capacitor. So we can rewrite the expression for charge of a charging capacitor to be Q0 1 minus E minus T over CR. It's the same thing as me substituting Q over C in this expression. So it's like me saying Q over C, but then since capacitance is the same, it cancels out and you're left with this expression fully. In the exam, you will be given the formula booklet and you will only be given these two expressions. You won't be given these expressions. You won't be given the actual expressions in terms of QV and QV and I, or which capacitor or resistor that you're looking for the potential difference across each one of them. You will only be given this expression and this one. 1 e to minus t over CR. So this one works for all the discharging the capacitor equations, so for Q, V, and I. So for discharging Q, V, and I, but for charging is only for the current in the circuit and for the potential difference of the resistor. And for this expression is only for charging, and it only works for the potential difference of the capacitor and the charge stored on the capacitor. So be very, very careful. Exam questions always catch people out in terms, and even in multiple choice questions, in terms of their wording regarding the charging of a capacitor and this expression. This is the very, very important part of it. So that's the topic of charging and discharging a capacitor. We introduced a lot of new expressions, and for some of you, some new mathematical analysis that you will need to know for the course. Hope this was helpful, and if you would like me to do some exam questions, then do let me know and I will do some more for you.